Hi there! I hope that you're all doing very well and are just as pumped up for today's class as I am. I am your personal physics tutor, Dr. Rima McMullen, and I'm on a mission. And my mission is to bring quality level physics and mathematics education to everybody. I want to make everybody believe that they can too do math and physics. So far, these lectures are my first step in the direction of accomplishment of my mission. This is all my resources are allowing me to do for now, but this is just the beginning. I have long ways to go. I have a huge vision of how to bring good math and physics education to everybody, to help people improve their logic and reasoning skills, because that's what's going to take you forward in life. I want to instill a love of learning in all of us, including myself. Alright, with that being said, let's begin today's class. Today's class is based on Vernier Caliper. It's a tool for length measurement that looks something like this. Here you go. We're going to get into the details of this very soon, but before we do that, let's take a few minutes to talk about different kinds of tools that are used to measure length. Let's say we are asked to determine the volume of a book. For instance, the volume of this excellent physics book, An Advanced Introduction to Calculus-Based Physics, Mechanics by Chris McMullen. So how would you measure the volume of this book? To get the volume of the book, you have to measure its height, you have to measure its width, and you have to measure its thickness. So what kind of length measuring device do you think you would use to measure the three dimensions, the height, the length, and the width of the book? I'm sure you all agree that we'll use a ruler. Here's the book. You will use a ruler to measure its height, to measure its width, and to measure its thickness. And after we have these three spatial dimensions measured, we're going to multiply them together to get the volume of the book. So you will use a ruler whenever you're measuring the length of an object that is neither too small nor too big. Something that you can easily hold in your hands, a ruler will be a good candidate to measure the length of that object. However, yes, there's always a however. If you're asked to measure the length of something, let's say like this desk here I'm working at. So if I spread my arms in both directions, see like this, like a wing, even then my arms are not long enough to span this desk. So if I were to use a ruler to measure the length of this desk, I'll have to measure, okay, 1 foot, flip it, another foot, flip it over, another foot, or however you like to use your ruler. So I think we could all agree that ruler is not a very good length measuring tool when the length involved is like the length of this desk over here. I expect this desk to be what? I think it's about 1.5 meters long or so. In such a case, what you could use instead is a tape measure or a measuring tape. So this measuring tape and a ruler, they're both calibrated, they're both marked in centimeters and in inches. So let's next talk about the least count of these two tools. What is least count? Least count is the smallest division on the tool, smallest that the tool can measure. So what do you think is the smallest that a ruler can measure? You got it right. It is this division over here. Let's mark it over here, right here. This distance. What is this distance equal to? 1 millimeter. Sure, the measuring tape is calibrated, it's marked in inches, and the ruler is also marked in inches, not this particular ruler though. We're going to ignore inches. Throughout this lecture, we are going to stick with metric system of units. Hopefully you know what's metric system of units. It's a system that is based on powers of 10, like centimeters, meters, millimeters, kilometers, etc. The least count of a ruler is, I already just told you and you already knew it, it is 0.1 centimeter, same as 1 millimeter. Okay, so this was a ruler and a tape measure that can measure something such as a book that may have a height of 12.9 centimeters. So you can see that it is going to one digit after the decimal. Is it very accurate? Is it very precise? Not really. If you want to have greater precision, you want to have more number of digits after the decimal. You want to go to a higher decimal place. And for that, you're going to use a Vernier Caliper. What is a Vernier Caliper? Looks something like this. We're going to get into the mechanics of this, how the measurements are made using a Vernier Caliper in this lecture, but for now, all we are looking at is what are different kinds of length measuring tools and what are their least counts. So what is the least count of a Vernier Caliper? It is 0.01 centimeters. Remind me, what was the least count of a ruler? The ruler has a least count of 0.1 centimeters. So the Vernier Caliper's least count is 10 times smaller than the least count of the ruler. You will say that the ruler's least count is 1 order of magnitude greater than the least count of Vernier Caliper. Or you could say just as well that the least count of Vernier Caliper is 1 order of magnitude smaller than the least count of a ruler. Now you may ask, what does order of magnitude mean? Now you know that when I'm saying ruler has a least count of 0.1 centimeters, which is 10 times greater than the least count of the Vernier Caliper. So it is 10 to the power 1 times greater than the least count of the Vernier Caliper. This power 1, it is the order of magnitude. Okay. So when we're comparing the order of magnitude, we are looking at, we're comparing two quantities by using factor of 10. One is greater or smaller than the other by a factor of 10 to the power something. That power, that is the order of magnitude. We're going to look at some more examples of order of magnitude as this lecture progresses. Okay. Now, this is one kind of Vernier Caliper. We could have more sophisticated Vernier Calipers where the least count could be 0.02 centimeters. Or we may have even more sophisticated Vernier Calipers with order of magnitude as small as 0.005 centimeters. It's quite small as compared to that of a ruler. Okay. So this is the least count or the least counts of the Vernier Caliper depending on what kind of Vernier Caliper we are using. This Vernier Caliper that I have over here, its least count is 0.02 centimeters. Okay. Alright, the next kind of tool that we're going to discuss that can measure something as small, as little as the thickness of a paper. So thickness of a paper, would you use a ruler to measure it? Absolutely not. Would you use a Vernier Caliper to measure it? No, you wouldn't. It wouldn't be a good tool for that. How about if you were to get the, I can't even see it in the camera here, the thickness of one strand of hair. Can you see it? Nah, not really. Anyway, to get the thickness of one strand of hair, what kind of tool would you use? To measure distances, to measure lengths or thicknesses, very, very small as one strand of your hair or thickness of one sheet of paper, you would use a micrometer, also called as a screw gauge. So let's talk about the least count of a screw gauge. What is the least count of a screw gauge? A screw gauge's least count is 0.01 centimeters. Now you might say, we just saw that a vernier caliper, it can have a least count of 0.01 as well. Not just that, we saw that vernier caliper could have least count as small as 0.02 centimeters and even 0.005 centimeters. Those numbers are much smaller than this number. Then how is it that screw gauge can measure something even smaller than a vernier caliper? It can. Because this least count here is the least count of a given kind of micrometer. You could have another kind of micrometer that can have a least count of 0.001 centimeters, which is definitely smaller than what? 0.005 centimeters, which was the least count of a very, very good vernier caliper that could measure distances as small as they can. Alright, so this is what? This is a screw gauge and a micrometer. After I'm done with my lecture on vernier caliper, some problems of it, then my next lecture is going to be based on micrometer. So stay tuned. Micrometer or screw gauge. Its lecture is coming up pretty soon. Now this was about small things such as the thickness of a paper or thickness of one strand of hair. But is screw gauge the only tool that I could use to measure the thickness of one strand of hair? No. I could use an optical microscope. Now some of you might claim that microscope that is used to look at objects. Sure, microscope is used to look at objects that are very, very small. Optical means light. We're using light to look at objects that are very, very small using an optical microscope. So the light falls onto the object, it reflects from the object, comes back to us, and we look at the object. But microscope can not only look at the object, it can also measure the length of the object. Okay. An optical microscope can magnify. It can make the object look larger by a factor of 5, 10, 20, 50, 100, 500, 1000, and even up to 2000 times. So microscopes are indeed very handy and they are very useful in labs. Okay, so what is the least count of a microscope? The word in itself has the term micro. So it should be able to measure objects of the length, whose length is of the order of micrometers. So you would think that an optical microscope, it should be able to measure the length of the objects that are of the order of micrometers. So the least count of an optical microscope, that is 10 micrometer. Not just that. It can measure something as tiny as 1 micrometer. Now what is 1 micrometer and 10 micrometers in terms of centimeters? Why in terms of centimeters? Because when we looked at the least count of a ruler, vernier caliper, and screw gauge, they were all in centimeters. So just to make the comparison a little more, visible, or be able to understand the comparison a little more concretely, it's good if everything is in the same units. So 10 micrometers. 10 micrometers, if I were to change this into meters, this will be 10 to the power negative 5 meters, which is same as 10 to the power negative 3 centimeters, which is same as 0.001 centimeters. Now you might say, hey, this is same as that of a screw gauge. Sure it is, but again, that was a high-end screw gauge, and this is a low-end microscope. Same way, the high-end vernier caliper's least count is same as that of a low-scale screw gauge. Okay, next is this 1 micrometer here. What would this be in centimeters? this will be 10 to the power minus 4 centimeters or 0.0001 centimeters. So now here we can see that this is smaller than the least count of screw gauge. Okay, this was an optical microscope. But do we sometimes have to look at objects or measure the lengths of the objects that are even smaller than a micron? Sure there are, especially if you're looking at some viruses that can be very small, or very commonly in the electronics. There was a time of microelectronics. Now we are into nanoelectronics. And when you make those circuits, you have to look at them also. What do you use to look at them? You use optical microscopes to look at large scale structures. And you use something called a scanning electron microscope to look at very, very small structures. Now, scanning electron microscope, instead of light, you're using electrons to probe the structures. Very high energy, very high speed. Electrons that are going to hit the substrate whose image you're trying to take. And these electrons will be, some electrons will be reflected, some will be transmitted, some are scattered. So those reflected, scattered electrons, they are captured by detectors. And those detectors then make the image of the object, whatever you're looking at. For example, these images over here. So these scanning electron microscopes, their least count can be 10 nanometers or as small as 1 nanometer. So here I have already written it down that 10 nanometers is 10 to the power minus 6 centimeters. And if you write that in terms of decimals, you will get 0 decimal followed by 5 zeros and then a 1. That's in decimals. And 1 nanometer will be 0.6 zeros and then a 1 centimeter. So you can see, as compared to a ruler or even a Vernier Caliper or even a micrometer or even an optical microscope, this is very, very tiny. I mean, if you talk about 1 nanometer, it will have 10 hydrogen atoms. Hydrogen is the smallest atom. So only 10 atoms are enough to fill some distance as small as 1 nanometer. So 1 nanometer is a very, very small scale length. Not just this. We're not done. We can measure length even smaller than this. And when you're talking about even smaller, 1 order of magnitude smaller than 1 nanometer, you're in atomic realm. We're talking about the scale of 1 hydrogen atom. And sure, even that can be measured using scanning tunneling microscope. So scanning tunneling microscope, this too uses electrons, and its least count is 0.1 nanometers, which is what? 1 angstrom, which is the size of 1 hydrogen atom. So these are atomic scale measurements. And this is one of the most precise instruments available on Earth. Not just that, this is based on quantum tunneling. So SEMs, scanning electron microscope, STM, scanning tunneling microscope. These microscopes are very precise, they are very accurate, and they are very sensitive. Especially this STM over here. You can't even walk around this. If you walk around it, it's going to capture that noise. And you're going to get artifacts like the false images. So these tools, like I already said, these are very, very precise, very sensitive tools, and they're also very extremely expensive tools. These can run in millions of dollars. Okay, now so far we have been talking about small things. But are there only small things that need to be measured? Absolutely not. We also measure large-scale objects. We measure celestial objects in celestial distances. For instance, distances between galaxies, distances between stars. What kind of tools do we use to measure those kind of distances? I bet you all know it. They are telescopes. So telescope is not the topic of this class, so I'm not going to talk about this. But let's very quickly look at the different kinds of tools for length measurement that we have looked at so far in this lecture and what are their least counts. So what did we begin with? We began with a ruler or a tape measure. Then next thing we looked at was Vernier Caliper. And then we looked at a screw gauge, also called as what? A micrometer. Then we moved on to optical microscope, followed by an SEM, scanning electron microscope, then a scanning tunneling microscope. What did we say the least count of a ruler is? 0.1 centimeters. Vernier caliper, 0.01 centimeters. Screw gauge, 0.001 centimeters. Optical microscope, 0.0001 centimeters. SEM, 0.0000001 centimeters. STM, 0.0000001 centimeters. So if you talk about the order of magnitude, then there's a difference of one order of magnitude going from ruler to vernier caliper, another one order of magnitude going from vernier caliper to screw gauge. But going from ruler to screw gauge, there's 2 orders of magnitude difference. Going between screw gauge and optical microscope, 1 order of magnitude difference. And going between ruler and optical microscope, 3 orders of magnitude difference. While going between optical microscope and an SEM, how many orders of magnitude difference? 3 orders of magnitude. And SEM to STM, 1 order of magnitude. Optical microscope to STM is going to be 4 orders of magnitude. And going from ruler to STM holds 7 orders of magnitude difference. That is an insane amount of order of difference. Wow. 7 orders of magnitude. That's awesome. All right. Now we have looked at different kinds of tools for length measurement. We're next going to dive into the actual topic of this class, which is vernier caliper. Let's look at that. Let's talk about vernier caliper now. Vernier caliper was invented not by an engineer, not by a physicist, but by a mathematician, Pierre Vernier. He was a French mathematician who invented vernier caliper in the year 1631. That is almost 400 years ago, during times when there was no light bulb, no modern machines, nothing. Back in those times, Pierre Vernier, he invented vernier caliper that we are using till this date. Okay, so this tool, vernier caliper, it has high accuracy and high precision. Now we have talked about precision and accuracy in the previous lectures, but just to give you a quick reminder, if a given measurement is close to its true value, then we say that the measurement is accurate. The closer the measurement is to the true predicted value, the more accurate the measurement is. And if given measurements of a single quantity, they're all close to each other, then our measurements are precise. So a vernier caliper has both high accuracy and high precision. Okay, so that was that. Now we know who invented vernier caliper, and we know that it has high accuracy and high precision. And we already said that it is used to measure length. But what kind of length are we actually talking about? It can be used to measure 3 kinds of lengths. It can be used to measure external measurements, internal measurements, and depth measurements. What do we mean by these? Let's see. So what I have here is, I have an empty container. Here you can see it. And I have a vernier caliper. Okay. This container, it has two kinds of diameters. It has an external diameter going around the edge of it on the outside, and it has an internal diameter. So this vernier caliper can be used to measure the external diameter using external jaws. Okay. Let me show it to you what I mean by this. Here, I am measuring the external diameter of the container using external jaws. The longer, the big jaws. Those are the external jaws. Not just that, I can measure the internal diameter using the internal jaws. Let me show it to you. Give me a second. Here, got it. Here we go. You can see. Now these smaller jaws, they're on the inside of the container. So they are measuring what we call as the internal diameter of the container. Not just that. This container has some depth. See, it has some depth. My fingers are going into it. So the depth can be measured using this drop down. Here. See how it moves up and down? So what you will do is you will drop down depth rod into the container. And by doing so, you're going to measure the depth of an empty container, a hollow container. Alright, so these are the three kinds of measurements that can be made using a vernier caliper. Okay, what's next? Where is it used? Now we know that vernier caliper can measure three kinds of measurements, but where does a vernier caliper find its applications? So where do vernier calipers they find their use? They are used in engineering and machining, of course. They are used in mechanical workshops. They are used in manufacturing industries. They are used in laboratories, and they are used in educational institutes. So I work at a manufacturing industry. I do not personally use a vernier caliper there, but the equipment engineers, the engineers that are responsible for maintaining the tools, for making sure that the tools are working right, they're performing right, they use vernier calipers all the time. So what they have is, they have these digital calipers. They don't use the kind of caliper that we are going to discuss. Their caliper, they will just put it there, and there's a digital readout meter. It will give them the measurement. It makes their life easy. However, to actually know what's going on, how it is measuring, we have to go through the process that we're about to go through in this lecture. It is important to build our reasoning skills, build our logical skills. Only then we'll be able to catch any mistakes. Tools do make mistakes. Instruments do make mistakes. They get out of calibration. And until we understand how the tools work, we'll never be able to catch them, nor will be able to fix them. So it's important to understand the mechanisms, the mechanics of the things. And that's exactly what we're going to do in this lecture. All right. With that being said, let's look at this beautiful vernier caliper over here. I drew it myself. Of course, using the drawing tools, but it was still a lot of work. So in this vernier caliper, this yellow scale, it is called as the main scale. It is exactly the same as that of a ruler. It's basically a ruler, simple ruler that you and I and everybody else in the world uses. But you will see that this is not it. This is not the only ruler there is. We also have this tiny ruler here, over here. What do we call this one? We call this one as vernier scale. And this vernier scale, it is actually a sliding scale. I showed you the example of this Vernier caliper already, and you can see that I can slide it here. It's a sliding instrument. The vernier scale, which is located over here, down here, I can slide it. Alright, let me close it so I don't hurt myself with the depth rod. So we have two scales, main scale and vernier scale. Okay. Next we are going to look at these two external jaws. External jaws are used to make what? External measurement. Okay. Next we have these internal jaws. What are these internal jaws used for? We looked at that. The internal jaws are used to do what? To make internal diameter measurements. And then we have this depth rod over here. This is used to make depth measurements. Here is the depth rod. So here you got internal jaws to make the internal measurement, external jaws to make the external measurement, depth rod to make the depth measurement. Not just this, it also has this locking screw. So once you have your object held in place between external jaws or internal jaws or using the depth rod, whatever it is that you're using, you want to hold the vernier caliper in place so it doesn't accidentally slide. And to do that, you're going to use what? Locking screw. Okay. So this is the anatomy of a vernier caliper. Soon we're going to dive into the physiology, into the mechanism, into the mechanics of vernier caliper. Next, we are going to look at the part of the vernier caliper that I have put in white circle over here. So here I have enlarged it. Let's look at this. So on the top, on the main scale, one small main scale division equals how much? We know that it is equal to what? It is equal to 0.1 centimeters, or we can say that this is equal to what? 1 millimeter. Okay, very well. Then we're going to find out one small vernier scale division. That is equal to how much? So I have put that here. This is here, over here. This is one small vernier scale division. One small vernier scale division is this one here, between two small vernier scale lines. Okay. To figure out the value of one small vernier scale division, here's what we're going to do. We're going to look at the 0th line on the vernier scale and the 0th line on the main scale. And in this scale, you can see that the 0th of the main scale, which is the yellow scale, lines up perfectly. It perfectly coincides with what? The 0 of the vernier scale. Okay. What's next? Next, we are going to see that the last line of the vernier scale, which is the 10th line on the vernier scale, that lines up perfectly with what? The 9th line on the, here. This is the 9th line on the main scale. Okay. Using this, we're going to say that the 9 main scale divisions, they equal what? 0.9 centimeters. We know that because we know one small main scale division equals what? 0.1 centimeters. Therefore, 9 main scale divisions must equal 0.9 centimeters. We also just said that 10 vernier scale divisions equal what? 9 main scale divisions. So we're going to use that, and we're going to say 10 vernier scale divisions equal 9 main scale divisions. And we know that 9 main scales division equal what? 0.9 centimeters. Using this, we can say that one vernier scale division equals 0.09 centimeters. Now we know how much one vernier scale division equals 0.09 centimeter. This vernier scale division of 0.09 centimeters, that is for this specific vernier caliper. Different vernier calipers may and will, in general, have different values of the vernier scale division. Now we're considering a scenario in which what we have done is we have slid is a word, right? We slid this vernier scale just ever so slightly, like this. Initially, it's supposed to be like this. The two zeros are perfectly coinciding. Then we slightly move the main scale over to the right, very, very slightly, such that the first division, not the 0th, but the first division of the main scale coincides with the first division of the vernier scale. So, what is being done here? Over here, the vernier scale is slightly moved over to the right, such that the first division on the vernier scale coincides with the first division on the main scale. And hopefully you can see that. Let me show it to you over here. So when you slide it over to the right, okay, the zeros will get offset. And the first division that will actually coincide after moving it over to the right will be the first division. Okay, so that's all is done so far. Let's see what's next. Let's go to the next slide. Same thing, just enlarge it a little more, right? So what I'm going to do is I'm going to look at what is this offset's value. Now you can see that the 0 of the main scale doesn't coincide, doesn't line up with 0 of the vernier scale. What is the offset between the two zeros? Okay, that's my goal. So here's the goal. Figure out the value of the offset between the two zeros. One zero is on the main scale and the other zero is where it's on the vernier scale. Just to get a better idea, these black lines are quite wide, so we're going to look at the center of these lines. So now very easily you can see, it's very clearly visible that this is the offset in this pink line. And we want to get the value of this. How do we do that? To do this, here's what we can do. If you go from the 0 of the, here's the 0 of the main scale to the first division of the main scale here. What is this value? This value, let's call it as A. Okay, why not? Let's call it as A. What's the value of A? A is equal to 0.1 centimeters. Correct? And likewise, if I go from the 0 of the vernier scale, this is the 0th division, to the first division, now this first of the main scale and the first of the vernier scale, they are coinciding. And call this distance, okay, let me call as B. Okay, then what will be the value of B? B is equal to 0.09 centimeters. We just looked at it in just a few previous slides. And the value of A minus B, that gives you the value of this offset. Okay, and when you do 0.1, let's write it as 0 minus 0.09, what do you get? 0.01 centimeters. This is the least count of this Vernier Caliper. So what we have done essentially is we have determined the value of the least count of this Vernier Caliper by sliding the Vernier Caliper just slightly over to the right, such that the zero of the main scale and the zero of the vernier scale, they get offset, and the first division of the two scales coincide. And this offset between the two zeros, this is the minimum value that we can determine or we can measure using this Vernier Caliper. I hope it makes sense. If not, like I always say, rewind, rewatch. Rewind, rewatch. If it still doesn't make sense, then what do? You put that in the comments. And I will try my best to address all of your concerns and questions related to what we're doing. All right, moving on. What do we do next? This is basically the same slide. I suppose I put it here so I could show it to you that this is my A, this is my B, and my A minus B is equal to 0.01 centimeter, which is equal to the offset between the two zeros, the horizontal offset. So horizontal offset between the two zeros, one zero on the main scale, the other zero on the vernier scale, when the first division on the vernier scale coincides or lines up perfectly, coincides with the first division on the MS is the main scale. So if you had moved it so far as to have the second line coinciding or lining up, then you would not have least count, but you would have twice the least count. Try that. Okay, what is next? Let's see. Here is another kind of vernier caliper, an orange and a green one. In this caliper, we see that the zeros of the two scales, they exactly line up. And the 10th division of the vernier scale, it lines up with the 11th division of the main scale. So we're saying that 11 main scale divisions are equivalent to 10 vernier scale divisions. All right. So what does this give us? 10 vernier scale divisions are equal to 11 main scale divisions equal to 11 millimeters. Or if you want to write this in terms of centimeters, you could call this as 1.1 centimeters. Okay. What does this make one vernier scale division to be? That would be 1.1 millimeters. Okay. So the least count of this vernier caliper would be main scale division minus vernier scale division. 1 millimeter main scale division minus 1.1 millimeter for the vernier scale division. Is this positive or negative? This is negative. And negative least counts are not defined. So in case where we have a fewer number of vernier scale divisions corresponding to a certain given number of main scale divisions. For example, in this case, we have 10 vernier scale divisions corresponding to 11 main scale divisions. In such a case, your least count will be negative if defined this way. That is main scale division minus vernier scale division. And hence it is not defined. In this case, you will not have a least count for the vernier scale. What you will have is you're going to use the long elaborate method to make the measurement. How so? We're going to look at that. So, alright, we already said the least count of vernier caliper. This vernier caliper does not make sense. But we may still have this vernier caliper and we may be asked to make a measurement. For example, find out the value of the length of this biscuit that is held between the external jaws of the orange colored vernier scale. How would you do it? Let's see. So we know that the vernier scale division is 1.1 millimeter here. As per the rules, we're going to look at what? We're going to look at the zero of the vernier scale. Let me grab a black color. Okay, here's the black color. And let me also make it bigger. Here. Zero of the vernier scale. Does it line up with one of the main scale readings? In this case, it does not. So what we're going to do is we're going to look at the main scale reading that is immediately to the left of the zero of the vernier scale. And that happens to be 0.8 centimeters. So basically what we're saying is that we're sure till here that the length of this box is 0.8 plus whatever this pink line is. Let's call that as delta L. So 0.8 centimeters plus delta L, that is our measurement. So our goal is to find this delta L now. How do you find delta L? Okay. To find delta L, look at vernier scale divisions and figure out which of the vernier scale divisions best matches up with one of the lines on the main scale. And in this case, it's a perfect match of the fourth line of the vernier scale. Very good. Next thing we're saying is that to obtain this delta L, which is this here, what can we do? We can measure the length of A. A is going from this 8th line on the main scale onto this 13th line of the main scale. And then we're going to find B. B is going from the 0 of the vernier scale to the 4th line of the vernier scale. Once we can find this A and B, then to find delta L, this is your delta L here, or uppercase L. To find delta L, all you have to do is find A minus B. I hope you're with me so far. I hope it's making sense so far. If you have any questions, please ask me in the comment section. Alright, so our goal is to find the value of delta L, which is A minus B. And in this case, A is equal to 0.5 centimeters. How so? You can count for yourself. You start here. This is the first division, second, third, fourth, and fifth. And each of these main scale divisions equals what? 0.1 centimeters. So 5 times 0.1 gives you 0.5 centimeters. Next, we are going to find B. Now, B is going from 0 of the main vernier scale to 4th line of the vernier scale. So there are 4 of these divisions. So there are these 4 divisions on the vernier scale. And we said that each of these divisions is equal to 1.1 millimeters. So 1.1 millimeter times 4 is 4.4 millimeter, which in centimeters is 0.44 centimeters. So knowing the value of A and B, we could easily calculate the value of delta L, and from there we could calculate the value of L. So putting all the numbers in here, you can see that L is equal to what? 0.86 centimeters, which it seems to be correct. I mean, here, this is how long the length L is. And we can see here that it is greater than 0.8, smaller than 0.9, but it is closer to 0.9 than it's to 0.8. So 0.86 centimeters makes perfect sense here. I hope it does to you as well. Ready to move on to the next slide? Let's do so. Here is another kind of vernier caliper. Do we have a least count defined for this vernier caliper? Now least count is, we said it is 1 main scale division minus 1 vernier scale division. For this to be defined, it has to be a positive value. For this least count to be a positive value, main scale division's value has to be greater than Vernier scale division's value. And that would be true only when the number of Vernier scale divisions that are equivalent in length to whatever number of main scale divisions. The number of Vernier scale divisions have to be greater than main scale divisions. I know, a lot of words. What do I mean? Let's see. In this case, we have how many Vernier scale divisions? 11. Going from here to here. They line up, or they are equivalent in length to how many main scale divisions? 10. So we see that this 11 number of Vernier scale divisions that are equivalent in length to 10 main scale divisions. 11 is greater than 10. So in this case, a least count will be defined. Why? Because 11 is greater than 10. That's going to make a Vernier scale division smaller than a main scale division. How? Let's see. Okay, so we said that 11 Vernier scale divisions equals 10 main scale divisions equals 10 millimeters. From here, we can easily determine the value of one Vernier scale division. That would be equal to 0.91 millimeters. Alright, from here, can we determine the value of the least count, which is equal to 1 main scale division minus 1 Vernier scale division. That's going to be equal to 1 main scale division is 1 millimeter, 1 Vernier scale division is 0.91 millimeters. So that is equal to 0.09 millimeters. Equivalently, it is 0.009 centimeters. So this is our least count. Now using this same caliper, we're going to figure out the value of this measurement. Let's see. First step of the strategy. Look at the 0 of the Vernier scale. Does it exactly line up with any one of the main scale divisions? In this case, it does not. Then you're going to take the division immediately to the left of the 0 of the Vernier scale as your main scale reading. To get your Vernier scale reading in this case, where a least count is defined, you're going to start out the same way. You're going to find out which of the Vernier scale lines best lines up with one of the main scale lines. And I say that's going to be this one here, 7th line. So this n over here, that is equal to the 7 over here. And least count we already know is 0.009 centimeters. This was our least count. So our measurement will be main scale reading, which is equal to 1.1 centimeters from here. 1.1 centimeters plus n is equal to the 7 over here. This is the 7th Vernier scale line that best lines up with one of the main scale lines. 7 times the least count is 0.009 centimeters. Okay. Just making sure that the least count was indeed 0.009 and I was not misremembering it. Alright, this gives us 1.1 centimeters plus 0.063 centimeters equals 1.163 centimeters. So as you can see that the actual reading lies between 1.1 and 1.2, but it is greater than, it's more toward 1.2 than toward 1.1. And when you look at this value over here, 1.163, that is closer to 1.2 than is to 1.1. So hopefully this example made sense as well. Let's see what the next thing is, what the next slide says. I hope that by now you have developed a good sense of how to determine the least count for any given vernier caliper. So here's another vernier caliper for you guys, and my recommendation to you is that you pause the video and determine the least count of this vernier caliper on your own, and then come back and resume the video to see if your answer is correct. Like I always say, physics and mathematics, they are not spectator sport. Alright, with that being said, this is how I will solve this problem. Step number 1. So in this case, we have 50 vernier scale divisions are equivalent to 49 main scale divisions. And each main scale division is equal to 1 millimeter. So we get that 50 vernier scale divisions are equal to 49 millimeters. From this, we can very easily determine the value of one vernier scale division. How? By dividing both sides by 50. What does this give us? This gives us one vernier scale division equals 49 divided by 50, which is equal to 0.98 millimeters. So now we have the value of one main scale division, which is 1 millimeter, and one vernier scale division, which is 0.98 millimeters. Can we determine the value of the least count? Sure, we can. In this case, main scale division is larger than vernier scale division, so we can figure out the value of the least count. And that is going to be 0.02 millimeters. Same as that of 0.02 centimeters. Easy breezy. Ready to move on to the next slide? Alright, let's do that. We have yet another vernier caliper over here. What is the least count of this vernier caliper? In this case, you will see that we have 10 vernier scale divisions that are equivalent to 10 main scale divisions. Here, 10 vernier scale divisions equals 10 main scale divisions. This implies one vernier scale division equals one main scale division, which is 1 millimeter. So least count, which is main scale division minus vernier scale division, is going to be what? That's going to be 0. So this vernier caliper, this is not going to add to accuracy or precision of the main scale. This is actually an utter nonsense. Why? Because you will see that, you will notice that when you slide this vernier scale, either none of the vernier scale lines will line up with any of the main scales, or they will all line up, like this here. All line up, or none line up. And here, again, they all line up, or none of them lines up. So this doesn't make any sense. This is not giving us anything useful. I just wanted to show you that the magnitude of the vernier scale division cannot be same as the main scale division. If it is, then it's giving us nothing useful. It's not adding to the accuracy or the precision of the main scale. Okay, so that was that. Now we're going to move on to another kind of vernier caliper, which is this. So in this case, we're again asked to determine the least count of the given vernier caliper. Alright, so the 0 of the vernier scale lines up with the 0 of the main scale. That is good. We have 10 divisions on the vernier scale. They are equivalent to how many main scale divisions? 8 main scale divisions. And each main scale division is what? 1 millimeter or 0.1 centimeters. So from here, one vernier scale division equals what? 8 divided by 10 millimeters, right? Which is equal to 0.8 millimeters or 0.08 centimeters. Okay. Can we determine the value of the least count? How do we define least count? Main scale division minus vernier scale division. We said main scale division is 1 millimeter and vernier scale division is 0.8 millimeter. What does this give us? 0.2 millimeters, which is equal to 0.02 centimeters. Very good. Now we have the least count of this vernier caliper. Next, we are going to have the same vernier caliper. I have just changed the colors here. Okay, it's the same one. Hopefully this makes sense now. Does it? If there's anything I could do better to make these lectures better for you, to make them more understandable, please do let me know. I'm all ears. Next, we are going to use the same vernier caliper and figure out the reading of it. Okay. Step number 1 is always the same. Look at the 0 of the main scale. And the 0 of the main scale doesn't quite line up with the 5th division of the main scale. So the division that's to the left of the vernier scale is 4th division. So your main scale reading is 0.4 centimeters. Okay. Next, you're going to see which of the vernier scale lines up with one of the main scale lines. And to me, it seems that the 4th line as well as this 9th line, it's hard to tell which one is better. Let's see what the 4th line gives me and what the 9th line gives me. If n equals 9, let n equals 4. Then the measurement will be main scale reading plus n times least count. Main scale reading is 0.4 plus n is 4 times 0.02 centimeters. This is all in centimeters now. This gives me 0.4 plus 0.08 equals 0.48 centimeters. And that could be correct. Why? Because this is 5. So this is actually 0.5 centimeters. This 10 here is actually in millimeters. Okay? I should have mentioned. Millimeters. Alright. Next, if n were this 9 instead, then the measurement will be 0.4 plus 9 times 0.02 centimeters. Gives us what? 0.4 plus 0.18. That gives us 0.58 centimeters. Now you tell me, does this make sense? Is our reading 0.58? No, it is not. So in this case, we have to take into account the first coinciding line. Because we have the 4th and the 9th, they looked about the same. But the 9th line gives us totally wrong answer. It doesn't make sense. We have to take this n equal to 4 in this case. Make sense? Alright. I hope it does. Moving on to the next slide. Now we're going to look at a new topic, which is the zero error of a vernier caliper. What does zero error mean? Zero error means that this vernier caliper gives us a non-zero reading even when it's measuring nothing. Even when its jaws are completely closed, it's measuring a non-zero reading. And that you can see if you look at the 0 of the vernier scale, that doesn't line up with the 0 of the main scale. Let me show it to you on the next slide by zooming in on it. So here, the 0 of the main scale and the 0 of the vernier scale, they're not quite lining up. And when that is the case, we have a zero error. And the zero error could be a positive zero error or a negative zero error. depending on whether the zero of the vernier scale lies to the right of the zero of the main scale or it lies to the left of the zero of the main scale. A good way to understand this is by looking at the number line. Here's the zero of the number line. All the numbers that are to the right, they are positive. All the numbers that are to the left are negative. In this case, we have the zero of the vernier scale, which is here, this zero. It is to the right of the zero of the main scale. Therefore, it is a positive zero error. But that is not the only way to understand it. Let's look at how else we can understand it. Now the question is, what is the impact of zero error on our measurements? How does it impact our measurements? Why should we care about it? We need to care about zero error because when we measure something on it, and let's say it says that it is 4.9 centimeters. But is it really 4.9 centimeters? This value is overexpressed. It is actually 4.9 centimeters minus whatever this zero error is, because this vernier caliper is showing that the length is already this delta L, even when there is nothing being measured. So from the measurement, we have to subtract this delta L. Make sense? Only then we'll have the correct value. How do we determine this delta L? Just like we have been doing. Figure out which of the vernier scale lines matches up exactly or best with one of the lines on the main scale. And in this case, it is number 3. Alright, so this line number 4, its distance is A from the zero of the main scale, and the fourth line's distance is B from the zero of the vernier scale. To get the magnitude of the zero error, what you have to do is you have to figure out A minus B. And in this case, it is very clear that A is larger than B. Therefore, the difference between A and B is a positive difference. Therefore, it's a positive zero error. However, to correct for the zero error, you have to subtract it from the actual measurement. So what happens is that in this case, the measurement is going to read larger than the actual dimensions of the object that is being measured. How come? Let's say delta L is what? It was A minus B, okay, and A was, alright, let's calculate this value of A minus B. A is equal to 0.123, 3 millimeters. And B is equal to 3 times 0.09. And B is equal to 3 times 0.9 millimeters. So that gives us 3 millimeters minus 0.27 millimeters, not meters, which is equal to what? 0.03 millimeters, equal to what? 0.03 centimeters. This is the value of the zero error. Now what we are saying is that if I make a measurement and my measurement is, okay, let me write the value of the zero error here. Here's our zero error. Let's say you made a measurement and your measurement turns out to be 4.24 centimeters. Okay. This is overexpressed. The actual value, M actual, would be 4.24 minus 0.03 centimeters, 4.21 centimeters. Why? Because this vernier caliper, it was reading a value of 0.03 even when it had nothing being measured, even when its jaws were completely closed. It's like saying you have a measuring scale for weight and it says 1 pound and you have nothing sitting on it. And then you place a child on it and it reads 20 pounds. What's the weight of the child? Is the weight of the child 20 pounds? No, that's going to be 19 pounds because this was already there. It was already saying that it was 1 pound when there was nothing on it. So the actual weight is the weight measured minus the zero error. That is positive zero error. When the zero error is positive, you have to determine the magnitude of that zero error and subtract it from the value that is being measured. Okay? We're going to do quite a few examples of this in the next lecture. For now, I wanted to give you an overview of what it means and how to correct for it. Just like I said, to correct for it, you have to subtract the value of the zero error from the measured value. Okay. Now, is positive zero error the only kind of error possible? Absolutely not. The other kind of zero error possible is negative zero error. In this case, you will see that the zero of the Vernier scale, that is to the left of the zero of the main scale. Okay. Just like I said before, here's your number line. This is 0. All the numbers on the left are negative numbers. Since the 0 of the Vernier scale is to the left of the 0 of the main scale, it's a negative 0 error. And in this case, what we're saying is that, for example, it's easy to understand this with the help of example of a weight scale. Let's say you're measuring weight and somehow the weight says minus 1 pounds. How it says minus 1 pounds? Let's not worry about that. And now you place a child on it and it reads 20 pounds. What's the weight of the child? Is that 20 pounds? No, that's going to be 21 pounds because first the weight will have to come from minus 1 to 0 and then it will go from 0 to 20. So it has to travel a total of 21 pounds. Make sense? So negative zero error, you will find its magnitude and whatever the measurement is, you're going to add the value of the negative zero error to that. In this case, what's the value of the negative zero error? Let's determine that. A. What's the value of A? We're doing the same thing again, by the way. Figuring out which of the Vernier scale lines exactly or best lines up with one of the lines on the main scale. And turns out that's line number 3 on the Vernier scale, third division. Okay. All right. A is going to be going from 0 to the second division of the main scale, 0.2 centimeters. While B is going from 0 to the third division of the Vernier scale. So 3 times 0.09 centimeters. What does this give us? 0.27 centimeters. So the zero error would be negative because 0.2 minus 0.27. Negative 0.07 centimeters. And using this Vernier caliper, if you find a measurement to be 4.83 centimeters, this is what you measured. The correct value would be 4.83 plus 0.07 centimeters, which is what? 4.90 centimeters. So this is your negative zero error. So we have looked at negative zero error, positive zero error, and we're saying that when you have a negative zero error, the measurement that you're making is going to be smaller than the actual dimensions of the object being measured. Therefore, the magnitude of the zero error gets added into the measurement. I hope that made sense. Just a recap of the negative zero error, it reads smaller than the actual dimensions of the object being measured. The value being measured is smaller than the actual dimensions. Therefore, to correct for this zero error, to correct for this negative zero error, you have to add its magnitude to the value that is being measured by the vernier caliper. Alright, so in this lecture, what all have we looked at? We looked at first different kinds of tools of measurements, and their least count. Then we jumped on to vernier caliper. And we looked at anatomy of vernier caliper. What are different parts of vernier caliper? Then we looked at mechanism or the physiology of vernier caliper. Mechanism. We looked at how to find least count. We looked at even the brute force method of finding the value measured by a vernier caliper. Okay. Value measured by what? By a vernier caliper. Then we looked at zero errors. Zero error could be positive or negative. Positive zero error overestimates the measured value. So from whatever the measured value is, you have to subtract the magnitude of the positive zero error. While in case of negative zero error, you underestimate the measurement. The measurement is smaller than the actual dimensions. So to correct for the negative zero error, you have to add the magnitude of the negative zero error to the measurement. So these are all the different things that we worked out, that we went over in this lecture. In the next lecture, we are going to look at different kinds of examples. We are going to look at examples of how to find least count, which is defined in case where a main scale division is larger than a vernier scale division. Then we are going to also look at how to make a measurement using vernier caliper using the least count, and also how to make measurement when a least count is not defined. And least count is not defined in case where main scale division is smaller than a vernier scale division. Then we are going to look at next the zero errors. There's positive zero error and negative zero error, how to read them and how to correct for them. So we are going to go over an exhaustive list of all kinds of problems that can be asked on or can be made on vernier calipers in our next lecture. Until then, you keep studying, you keep working, and I'll keep working too. I'll see you again next time very soon.